Hi everyone, my name is David Sang. I'm a software engineer on the accessibility team here at Google, and I have here with me my colleague Volker, who is a visiting professor from the University of Birmingham. We're here today to talk to you about ChromeVox and some of the exciting work we've been doing to make reading of mathematics on the web possible. To tell you more about this, I'm going to hand it off to Volker for a brief introduction to the work, and I'll then come back for a brief introduction to ChromeVox in general. Volker.
Thank you, David. So my name is Volker. I'm a senior lecturer at the University of Birmingham in the UK. And I've been spending the last year together with the ChromeVox team here to make an effort in order to make scientific material that's out on the web accessible for people with visual impairments. And first we have concentrated on making mathematics accessible using ChromeVox. Now, why is that important? Well, one of the problems with scientific material is that it is a hurdle in education that many people that have visual impairments are excluded from having scientific material readily available as their normal peers would have, because it is much harder to make scientific material fully accessible. And particularly if you think about something like mathematics, it is not as straightforward as reading just regular text. Therefore, it is often very difficult to make it accessible using the average screen reader. Now, there have been a number of efforts in order to make particular mathematics accessible that is on the web. But these are generally efforts that require either particular special tools or particular plugins for special browsers. So what we have been trying to do with ChromeVox is making mathematics accessible in just a standard screen reader, so making effectively mathematics a first-class citizen in the world of accessibility. And we have done also, in addition, some special elements like particular exploration of mathematics that we believe are fairly novel, and we're going to demonstrate to you in the upcoming hour. Yes, so first we'll start with a general introduction to what ChromeVox actually is, before we then go into more detail how one can use it to speak mathematics, and also how one can in particular use it to customize how mathematics is being spoken. And for the general introduction, that's going to be done by David. David, please.
Thank you, Volker. Just to get everybody up to speed and on the same page, I'm going to give a demo of ChromeVox and its general features and functionality as a general screen reader. So for the past, I'd say 3 or so years, we've been developing ChromeVox, and ChromeVox is just a Chrome extension. So it's all written in JavaScript, and we have access to all the information that any other web page would. And this gives us a lot of things that ordinary screen readers don't get, and everything that they do get. So we've been able to create something that I think is fully featured and allows a blind user to navigate all of the web. So to start off with, I will show everyone a standard page from Wikipedia. This is a square root. The topic for this page is on square roots. And I will start off by simply tabbing around and letting everyone hear the type of feedback we provide.
Navigation, internal link. This page has one alert. Do you want Google Chrome to save your password?
So there, you've heard quite a few things. So it says a lot. It says, first of all, the first thing that you've heard was navigation and a link, internal link. So those bits of information are contextual, and it tells you what the currently focused item is. So a user who's using a screen reader can then know how to interact with this. So since it's a link, one can press it and therefore land in another place on this page, since it's an internal link. And the second bit of feedback you heard was an alert given by the Chrome browser. So we actually speak that as well. So Besides landing on focusable items, we can actually move about the page and move to things that aren't focusable. So you do that by pressing the ChromeVox modifiers and the arrow keys. So let's hear what that sounds like.
Comma. Search, internal link. Quote square roots, quote redirects here. For the music festival, see. Square roots, link.
And you hear quite a few other things there. There were some static pieces of text, there were some more links, and one other item that is kind of interesting to point out is you heard a sound effect, kind of like a ding sound, and that actually represents a link. So whenever a user hears that, they automatically know that they can click on it. So some other interesting things are that a user doesn't necessarily have to go item by item. They can actually jump from section to section, and that's done via another keyboard command. And let's hear what that sounds like.
Contents, heading 2.
So there, I just skipped a lot of material on the page and was able to jump right to the contents listing. So let's try that again and see if we find anything else interesting.
Properties, heading 2.
All right, and keep on going.
Left bracket, edit source, link. Pipe, edit meta, right bracket, link. Enlarge the graph of the function, f, left parenthesis, x, right parenthesis, equals, square root of, x, math.
And there we have something that alludes to the rest of the talk, and it's how we actually make it possible to read that expression and make it possible for ChromeVox and the user to then communicate using something that's a little bit richer and a little bit more unique. So with that, one last thing to show is we can actually read content continuously just by pressing another command, and it'll actually read it kind of like a book from this point on to whenever you want to stop it.
Made up of half a parabola link with a vertical directrix link dot. The principal square root function f left parenthesis x right parenthesis equals square root of x math. Usually just referred to as the quote square root function quote as I function.
And I'll just stop it there. And that overall gives you a flavor of what ChromeVox is and what it does and how the user would use it, and a little bit of a taste of how math works and spoken math sounds like. So with that, I will throw it back to Volker, and he will continue on with some of the more interesting things that we're doing with math and how this is all possible.
Thank you, David. So, as you could already hear when David was demonstrating the continuous read of on the previous paragraph, there was math contained in the paragraph, and the math was just being spoken out in a fairly verbose way. We'll talk about that in a bit later, why this is so verbose. And in order to explain how that is being spoken out, it is probably worthwhile going a bit into detail how math is actually represented on the web. And particularly for those who are not fully aware how math on web pages works or should work, I'll give a quick introduction on that now. So ideally, mathematics on the web is represented by a special markup language called MathML. MathML has been around for some time, and it has evolved and matured to a degree that it's now been made a standard for HTML5, and as a consequence also for EPUB 3. So in other words, every EPUB 3 reader in the future should also be able to deal with MathML. Now the question of course arises, why is there a specialist markup language just for mathematics? Well, the reason is that mathematics is fairly involved in terms of the way expressions are being set up and how they're being structured, which is normally not doable or not easily doable with just regular HTML. In particular, think about that, regular HTML is very good with dealing with text and these things. It can also do sub and superscripts. However, as soon as things become more involved, as in a mathematics expression, which is by nature effectively two-dimensional and very, very nested, HTML alone can normally not deal with it. Therefore, MathML provides all the basic functionality, or rather the basics tags in order to create complex mathematics expressions and display them on the web. Now, while it is in general a good thing that MathML is fairly mature and that it's part of standards, what is a drawback about MathML is that it is not implemented in all browsers or all EPUB 3 readers. As a consequence, there are several ways of getting mathematics on the web to work nevertheless. So one of the ways is done by many sites such as Wikipedia by default, as well as other pages, is that one actually displays an image of the mathematics instead of having a MathML expression in there. And therefore it can be easily read by people who can actually see the image, but it cannot necessarily be picked up by a screen reader. Now, the advantage of this is sometimes that the real mathematics is still provided somewhere in the background, not visible, and therefore it can indeed be used by a screen reader, and I'll demonstrate to you later how that is being done. The other way of displaying mathematics on all browsers and all platforms is by using a little library called MathJax, which is done by the MathJax Consortium, and if you want to see check this out, this is at mathjax.org. And the way this works is that MathJax can be injected in any page that contains mathematics, and it's JavaScript, and it just renders that mathematics, which is either given as MathML or in a more traditional markup language like LaTeX or ASCII math, and it then renders the mathematics. Now, the challenge what this poses for a screen reader who actually wants to use the mathematics in order to speak it is that we actually have to deal with all these types of mathematics as they can occur. So we have to be able to deal with just standard MathML expressions as well as expressions rendered by MathJax, or expressions that are just hidden somewhere in an alternative text behind the image. And I'll show you now how that actually works in practice. Right, so let me just quickly demonstrate how this is then spoken by ChromeVox. So let's go to the first math expression again in this paragraph.
F left parenthesis x right parenthesis equals square root of x math.
As you can see, obviously the first math expression here in the DOM is actually the math expression which is in the caption of this particular image. But it's still spoken, and it went to it, and you can see it's being indicated by this highlighter, which is, for instance, particularly helpful if you need to see where you are in the text. So, for instance, if you're dyslexic, for dyslexic students, it's useful. And we'll just go to the next math expression, which should now be this one in the paragraph.
X right parenthesis equals square root of x math.
Right. And now, as I said, this works now nicely because I'm actually logged into Wikipedia. And if I were to now log out of the Wikipedia page, I then would get it just as an image. And it would still work because we can use the alternative text which is in the background, which is actually the LaTeX expression which you saw at the beginning before the MathJax was rendering. Now, I'm not going to log out of this Wikipedia page because we will need it later. And however, let's go to a different page where we have a similar effect.
From Wolfram Math.
And this is MathWorld, which is a particular encyclopedia just for mathematics. And what happens there is that you have the mathematics given as image only, always. However, you also have alternative text, and in that case, it's ASCII math. And we can leverage this ASCII math in order to pronounce it. And just to show you that the math expressions here are indeed images,
Algebra greater underscore than sums.
I'll grab it quickly and I'll move them around. See, so this is an image, and I can take this sum and just move it around on the screen here. And all these are images.
A sum is the result of an addition. For example, adding 1, 2, 3, and 4 gives the sum 10, written. 1 plus 2 plus 3 plus 4 equals 10, full stop, math.
So you could hear now that this is indeed a math expression. Although it was an image, it's being fully pronounced because we can leverage the alternative text. And you could hear also why it was a math expression, because it was specially announced using an earcon, as well as in the end an announcement that this is a math expression. Similarly, we can go to the next math expression, for instance.
K equals 1 under and 4 over an area summation. K equals 10, full stop, math.
So again, this is the math expression, how it's being spoken at the moment. And this now gives us the possibility to have math spoken that's on Wikipedia, even without logging in, as well as on MathWorld, as well as on many other sites where there's a similar effect. So for instance, there's many math blogs out there. So one of the blogs I'm going to demonstrate you is a famous blog from a famous mathematician, Terry Tao, who is a field medalist winner, and he regularly blogs on his latest mathematical research, and he does it in a similar vein to what we've just seen on the MathWorld side, that the mathematics is actually given in images. And I'll grab one of those images here and move it around so you can see that this is an image. So this is an image. Here's another one. But the alternative text in the background is indeed LaTeX, and therefore we can actually speak it using ChromeVox. So let's just speak this first definition, for instance.
Definition 1, multiple dense divisibility. Let y greater than or equal to 1, math. For each natural number, k greater than or equal to 0, math. We define a notion of k, math, to believe y, math. Dense divisibility recursively as follows. List with 2 items. Every natural number, list item, and math, is 0, math. To believe y, math. Densely divisible if list item, k, greater than or equal to 1, math, and...
Right, I'll stop it here. So what you could hear was that there was all the math in the paragraph has been spoken. Although it says images, we used the alternative text in order to translate it with the MathJax library. It's the same library we saw previously rendering the math on the Wikipedia page. When it comes back from the MathJax rendering, we can then use this representation in order to speak it. And however, we do this in the background in the sense that none of the content in the page is actually physically changed. So still it still has the same visual appearance as before. What you could also hear when we were speaking the math is that it was always giving a little earcon and a math an announcement, which gives you the possibility to actually find out where the math is. And this is in particular important if you want to have more interaction with the math. And this is our pass back to David, who's now going to explain to you one of the specialities of ChromeVox, which allows you to actually interactively explore a mathematics expression, which we believe is a very important step in order for people to fully engage with mathematical content that's on the web.
I think everybody can kind of identify with me personally in that hearing all of this is kind of a lot to take in. I mean, if you consider the often quoted figure of 7 plus or minus 2 bits of information that we as humans can kind of store and keep in our short-term memory, what we just heard was way more than 7 words. So what do we do about that? Well, speaking personally, I in the days when I was in high school and in university, used several methods to actually access mathematics. One primary way, and one that's pretty popular still, is to use audiobooks. And at the time, we actually used these 4-track audio tapes. So a tape which has 2 sides, and using both stereo channels, splitting those into mono, and having each channel record audio tracks. And someone, really, really nice volunteer, would sit down in a room and read through an entire math textbook. So this included anything from algebra all the way up to calculus and even beyond. I remember listening to a real analysis book in college, which was kind of one of lifetime experience. So it was really, really difficult, and there was a lot of rewinding and pausing and taking notes. So we feel like ChromeVox can do a lot better since we have a computer and we have the ability to write code to make things easier. So what have we done exactly? Well, think about any expression, and I'll demo this briefly later on, but just think about something that you've seen in the past, say the quadratic formula. How would you actually read that? It's not exactly obvious, and even harder is then to tell a person who's never seen it before kind of where all the pieces lie. So if you think of it like geography, where are all the countries and where are all the large pieces, where are all the continents, and if you want to dive into a specific region, well, what's inside there, and how do you actually give a quick summary of all of these things? And how do you actually let a person then ask you to describe something further? So this is kind of the challenge that ChromeVox has faced, and we feel like we've come up with a pretty good solution. So let me go ahead and just demo that for you now. We can hear how it does it now, and I can show you how a person would actually explore the various pieces of it.
We have x equals minus b plus minus square root of b squared minus 4ac divided by 2a math.
Now you immediately notice quite a few things. There are a lot of words, for one thing. We also slow down the speech rate quite a bit so that we can do some more intelligent things, like speeding up certain parts, slowing down others, inserting pauses, changing pitch. So one thing to add there is you'll notice a little bit of pitch drift. So all the stuff in the numerator you'll hear go up a little bit. All the stuff in the denominator you'll hear go down a little bit. And that power, the b squared, the squared part is actually up a little bit even more in pitch. So it kind of gives you another dimension to work with. So pitch kind of gives me, as someone who is the listener, an additional hint as to how high something or low something is vertically represented. But this is a still pretty beefy example if you remember your first algebra class. It's a lot to take in for someone who's seen this for the first time. So how do we actually let someone explore it? Well, we have one of these other ChromeVox commands that lets you go and dive deeper into this structure. So I'll go ahead and hit that.
Entered math x equals minus b plus minus.
And you heard that again. There was a sound icon that represents exploring something. And you heard the expression starting to read again, and I just stopped it for the sake of brevity. So how do we actually go and figure out what pieces are here? What's the general geography? Right. So there's this concept of granularities in ChromeVox that lets you zoom in and zoom out, essentially, of something on the page. So I'll go ahead and press that, and let's hear how that sounds.
Down to level 1, x.
So I just moved down a level, and I'm in a bigger chunk, not as big as the whole expression. So what is this? This is x, and it's obviously very important, so we let the user hear that in isolation. And we have some keys to move you around, and those are basically to move you forward and backward on the current level of things. So let's hear what that sounds like, and I will move forward.
Equals.
So equals is obviously also very important in this equation. So what's the next thing? And I'll go ahead and press next again.
Minus b plus minus square root of b squared minus 4ac divided by 2a.
And you heard again that whole big fraction. And you heard the pitch changes and everything else. And I will press the next key again.
Minus
Oh,
b.
and you heard a little sound, and that represents that we've bumped against an edge. So there's only 3 big chunks in this thing. And as a user that probably, perhaps never seen this formula before, well, I now have a really good sense of all the big pieces and all the big players here. But say I still am a little bit hazy on this fraction and I want to look a little bit more, I can actually dive in even deeper. So let's do that and hear that sounds.
Down to level 2, minus b plus minus square root of b squared minus 4ac.
And you heard the numerator. So that sounds great. And let's move forward.
2a.
And that's the denominator. So that all makes a lot of sense. And let's try moving forward again.
2a.
Up, bounced against an edge, move back.
Minus b plus.
Okay, we heard that before. Move back again.
Minus
up, another edge. All right, so we've gotten a really clear sense of where everything is again. So I can even dive even further, and let's do that real quick into this numerator.
Down to level 3, minus.
Okay, minus.
Minus.
Up. That's the beginning. So let's move forward instead of backward.
b plus minus
Forward.
square root of b squared minus 4ac. Square root of
Up, and
b
that's the
squared
end.
minus 4ac.
And if we really wanted to, we can even dive into the square root. So let's
Down
do
to
that.
level 4, b minus 4 a c c.
Yep.
A my b.
And that's it. So with that, it is our hope that students will be able to then really easily explore an equation like this that's now becoming possible with what we're doing with ChromeVox. And in the past, you would have had to rewind and fast forward through a tape and do it that way, or perhaps if you're really lucky, get math through Braille. But with the possibility of using online math, now you can get it in real time and look up a wealth of information on the web. So with that, I'll pass back to Volker, who will discuss some of the intricacies of actually applying some of these text-to-speech changes and the way we speak, and some cool stuff that you as a developer can actually do to improve any math that you might come across.
And I've previously mentioned earlier, at the moment, what we've demonstrated to you, the way things were spoken is very, very verbose in the sense that every single element is indeed being spoken out. Now that is not necessarily how mathematics is being spoken in real life. Right? Often you omit things although they're written. And this is something we can...
Mathematics.
I'm going to demonstrate a few examples where things are being very awkward when everything is being spoken, and where we then apply changes to our underlying structure and rule base in order to have them spoken more intelligently. And I will then afterwards tell you how this is actually being done and how that can be customized by users themselves or by creators of web pages. Right, so this is here Wikipedia page with a matrix example. So matrices are particularly difficult to speak because they are fully two-dimensional objects, and I'll show you at first how we can speak it in a full verbose fashion.
Left square bracket, matrix, element 1, 1, 1, element 2, 1, 9, element 3, 1, minus 13, element 1, 2, 20, element 2, 2, 5, element 3, 2, minus 6, right square bracket, full stop, map.
Right, so as you could hear, everything was being spoken here. Every bracket, every punctuation is being spoken. Now we have the possibility in ChromeVox to actually change the underlying representation in a way that we can get a bit more intelligence, a bit more semantics in there, if you like. And I shall do that now in order so you can see how this is being spoken then.
Matrix, row 1, column 1, 1, column 2, 9, column 3, negative 13, row 2, column 1, 20, column 2, 5, column column 3, negative 6, math.
Right, so as you can see here, the Chromebox is slightly more intelligent. It applies a slightly better way of pronouncing rows and columns, and in particular it omits some of the punctuation, which is not strictly necessary for a reader to know exactly whether this is a round bracket or a square bracket. In this particular instance, might not make any big difference. Right, these things can get particularly worse when the underlying representation is very similar, however the meaning is particularly different. So let's go back to our square root example, and I'll read you the first example here in the normal verbose style. Let's go to this case statement down here on the page.
Square root of x squared equals vertical line x vertical line equals left curly bracket matrix element 1 1 x comma element 2 1 if x greater than or equal to 0 element 1 2 minus x comma element 2 2 if x less than 0 full stop math.
So what you could hear now was that it not only spoke everything in a very verbose way, all the vertical bars as well as the opening brace, but it also, ChromeVox also found or fell into the trap that it saw something it thought it might look like a matrix, because it's exactly the same mathematical structure underneath as the matrix on the previous page, which I have demonstrated. Now, if we apply some slightly more intelligent way of reading this here, we actually get something slightly more sensitive.
Equation sequence square root of x squared equal absolute value of x equal case statement case 1 x if x greater than or equal to 0 case 2 negative x if x less than 0 full stop math.
So you can see here that what happened was that now, first of all, ChromeVox has a more semantic interpretation of the expression. It gives you a quick summary at the beginning. It's a sequence of equations, so there's more than two parts of the equation, and then it reads it in a more intelligent way by realizing something is an absolute value, as well as actually finding the case statement correctly, rather than pronouncing it as a matrix as it has done before. Right? And a similar semantic interpretation can then be applied to all the other statements. So if you go back, for instance, to this statement here and pronounce it first in the old way.
F left parenthesis x right parenthesis equals square root of x math.
Let's apply some semantics.
F of x equals square root of x math.
Right. So as you can see here, f, instead of pronouncing all the parentheses, we now say f of x, because we realize this is indeed a function application, and we pronounce it accordingly. Now, the way this is being done is by using an underlying speech rule engine, which allows for various ways of customizing the rule base that is being used in order to speak the mathematical expressions. And I'll explain very briefly how that works. Effectively, what happens is the math expression is, of course, a tree representation, and particularly it's a mathematical tree representation. And this representation is recursively being traversed, and in every node, a applicable rule is being computed, and that rule then has some actions which fire in the sense that they produce some speech output, as well as produce a way how to further recursively traverse the rest of the tree. And these rules can be customized in various ways. One way of customizing them is customizing them with respect to the mathematical domain. So what might be useful in one mathematical domain might not be the same in another mathematical domain. And when I say mathematical domain, what I actually mean is something like algebra, geometry, analysis, calculus, things like this. So you might want to pronounce one expression in algebra differently than in geometry. In addition to this, we have the possibilities of customizing rules by their style. And when I say style here, I mean something like, do I want it to be spoken short? Do I want it to be spoken in a verbose mode, for instance? Do I want it to be spoken in some particular way that I like and nobody else likes, etc.? And finally, we also have the possibility of swapping the underlying representation while it is being actually while the speech engine is active. So that's what I've just showed you. The underlying MathML representation here was swapped out with a more semantically enriched representation. Now, the problem with this semantically enrichment is, of course, is that this is a fairly ad hoc procedure. MathML is a language which primarily aims for display. So there's two types of MathML. One is called presentation MathML, and one is called content MathML. The idea of presentation MathML is that takes care of how the math expression is being laid out on the page. And this is what we're currently working with. The idea of content MathML is that an author of a math expression actually puts in some semantics. Unfortunately, that is hardly available on the web. Therefore, what we have to do is we have to take the presentation MathML expression and interpret it in a way that seems reasonable to us. Obviously, this can break down in many cases. And therefore, the person who actually knows best how to interpret a MathML expression is generally the author of the expression themselves. As a consequence, we believe that it is very useful for people to actually be able to customize their speech rules in a way that they will pronounce the MathML expressions they write in the correct way. We therefore in ChromeVox offer an API to users out there, to authors of web pages, to developers of EPUB 3 readers, that allows them to define their own math rules, either override or add to our rule base in order to have math expressions being spoken in the way they prefer. And the rest of the time I will now spend introducing this particular way of these particular rules, as well as demonstrate how they can be written and what the different components of these rules are. And for this purpose, I'll go back to to our favorite example, the quadratic formula. And we'll start manipulating the division in the formula in order to demonstrate how we can change rules. Right, yeah, I'll bring up the console quickly. Let me get back to... Let me get back to the expression.
Given, we have x equals minus b plus minus square root of b squared minus 4ac divided by 2a math.
Right, so this is the default way currently ChromeVox speaks the expression. I will now write a rule here in the console. I've already written it previously, so I'll just bring it up here and explain you the components that will just alter the way the expression is being spoken. Right, so what you can see here is in detail is that we have this function names is the way one can call ChromeVox through the API. So it's the ChromeVox API, it's the particular math API, and it offers a define rule function. And the function here at the moment has 4 components. All of these are string components. The first component is a name. It's practically irrelevant what that name is. The whole idea of name is that one can more easily find the rule later, somewhere in the speech rule engine, say for debugging purposes. But for now, we can just ignore this. So we just call this fraction rule. Then comes some admin information which has to do with the domain and the style I've been referring to previously. So the domain was, just to recall this, the idea that we can specialize our rules with respect to different mathematical domains, such as algebra, geometry, etc. In addition, we always have a default domain, which is the one we're working on right now, which means that if for a particular domain no rule is there, we can always fall back to the default rule. And currently the way domains are being selected is interactively by the user. Right, so this is what the default here says. Then we have a little dot which separates the domain name from the style name. And styles, again, we have styles like short, verbose, or I think we also have super brief. And but there is no limit to what you want to call your style. If you want to call your style after your personal name, then we have an additional style in ChromeVox in the future. And again, there is a default style. Here we're working now on the default domain and the styles short. Right. And then the rest of the rule is effectively a way how to test whether a rule is applicable, plus the action the rule is supposed to perform. In ChromeVox, this is given the other way around. We first start with the action and then with the precondition, or the rule that tests whether a rule, or the part of the rule that tests whether the actual rule is applicable. I'll tell you in a second why this is this case. Let's first have a look at this the letter part, which talks about the precondition. If the rule is applicable, what we want is a node, which is our fraction up here. Right? This division node is given by a mathml tag, which is called mfrac. And we select this using an XPath expression here. So this is a regular XPath expression, which just says, well, the current node, the node we are on, is a node with an mfrac tag in the mathml namespace. Right? So this is just a regular XPath expression. Then the rule will fire. And it will perform its actions. So what are the actions? Well, actions are a sequence of components of different things the rule does. In this case, we only have one component. And that component is currently composed from two things: the type of the component, as well as what is being performed. So the type of the component here is given in square brackets. In that case, the type is T, which means it's just a text that is being spoken. And the text that is being spoken is then given as a string here in string syntax with double quotes at the beginning and the end. So all we want is, when we find the division node, all we want at this point is a string being spoken that says some division. Let's put that rule in, and let's see what ChromeVox says
we
now.
have x equals some division math.
Right, that's all it says, some division. X equals some division. We haven't specified anything else. In particular, what we have not specified here is how it should deal with any of the other content that's still in the expression. So all we say at this point is say one string and then stop. Do not recurse any further. I'll show you in a second how we can do that otherwise. Let's first talk a bit more about the precondition. So the precondition here is an XPath expression, as I said, that selects this particular node with the mfrac tag. So it's this division node. Now, in addition to this, one can then give additional constraints, and the number of additional constraints is unlimited. Therefore, that's why this is the reason why we put the precondition at the end of this particular rule definition, because you can add more and more and more and more constraints to it. And I'll add one constraint just for you to be able to see how this will look like. So when we say, okay, so we want this rule just to be applicable to something that says that is the node itself, and it has a descendant which is an m square root, right? So that means it has a descendant which is a square root up there. And again, this is in the mathml namespace. Right, sorry, unexpected token means I have forgot to close my expression, my string expression with a parenthesis, with this quote. So let's see whether it's applicable. Well, this thing is that we haven't really changed any of this of the actions. So let's change the action so we can actually hear whether the different rule is being applied. Some division with square root.
Given, we have x equals some division with square root, map.
Right. So this has indeed worked, and it now applies the other rule. So we have specialized the rule even further. So in addition, we can now add more and more constraints. Anything XPath1 allows you to express, you can express in these constraints, and those are binary constraints. So they are either they only have to hold or not. Right. So this is as far as I want to explain the preconditions. Now let's examine a bit further what we can do in terms of the actions of our rule. In particular, just having one string pronounced if you actually have a complex expression is usually not very fruitful. So we might want to have a bit more pronounced. Therefore, let's dive into the expression and pronounce some of the child nodes actually. Right. So we now start a new component. Components are being separated by semicolons, so that's very similar to what you have in regular JavaScript. And we now want to specify a new component, and this is a particular component which works on single nodes. So therefore it gets the type n. Again, the type is being given in square brackets. And now we can write a selector which is just yet another XPath expression. So we write another XPath selector that selects whatever child we want to work on, or whatever node we want to work. It doesn't necessarily have to be a child. You can effectively also work on any other node that is reachable from this particular node you're on. But in our case, we want to work on a child, but let's not work on both. Let's just work on the second one, for instance. So this XPath expression now just selects from the given node the second child node. Right. And what the action now does is it will pronounce the string, some division with square root, and afterwards it will ask the speechal engine to recurse on this node that we have selected here. Let's do that again.
Given, we have x equals some division with square root to a map.
Right. So what you can hear is that we heard the expression up to the division, then it would pronounce the string, and then it would pronounce the second child node. Right. Similarly, we could now put in more content. So say we put in another string with of type T. Say this is now a string called enumerator. And we now, for instance, want to recurse on the first node as well. Oh, on the first child as well, not the first node. Let's do that. Let's listen to what's happening.
We have x equals some division with square root to a enumerator minus b plus minus square root.
I'll stop it here. We all know what the enumerator is, but you can see how this now works. Now, one of the things that David pointed out earlier was that you can actually do changes to the way the text-to-speech engine speaks things from within a rule. And let's do that. The way this works is by adding particular annotations to each component. So for instance, say we want to change the pitch on the first component that's being spoken, or in our case here's the second component of the denominator, and let's change, let's say we just want to have a significant pitch change, say to 1.5. Let's see how that sounds.
Given, we have x equals some division with square root 2a enumerator minus b plus.
So you could hear that the pitch was changed quite drastically when the denominator of the division was being pronounced. So the way we do these annotations is by adding in round brackets the particular property you want to change, as well as the value that changes it. Right, so in addition, we can, for instance, also increase the rate of the speech. Say we increase it to 2.5. And now let's see what's being spoken now.
X equals some division with square root 2a enumerator minus.
No, that was not really, that was maybe.
Simple school algebra, Volker Sorge, the 3rd of April 2013.
Sorry, that was not much of a change. I'll just refresh the console so we can see a bit more. Let's try to change it to something different. Maybe 0.5 will make a difference.
Given, we have x equals some division with square root 2a enumerator minus.
Now you could hear that it was actually quite a bit faster. So, so what else can we do with this? Well, another thing that we've heard earlier was that we can add pauses to our rule. Let's do that as well. Let's add a pause annotation, say to the second, to the first of these of the children that we speak. And let's add quite a drastic pause. Pauses are given in milliseconds, so let's add 1 second so we can actually hear it more clearly. So 1000.
Given, we have x equals some division with square root 2a enumerator minus b.
Right. So the effect you could hear here was something I wanted to demonstrate. It is that the pause, as well as all the other annotations, i.e. the pitch and the rate, that we give a particular a note here, or a particular component, are recursively being applied by the speech rule engine. That means if we change the pitch somewhere, this pitch change will be propagated further down in the recursive traversal of the tree. That means if we have nested expressions and we change the pitch several times, these changes will add up, which gives a very nice effect when it comes to pitch and rate changes. It doesn't really give a very nice effect when it comes to pause changes, because what that means is that the pause is applied after every single element that occurs. So you don't necessarily, you might want that, but you don't necessarily want that. So in this particular case, we don't. So how do we actually do it in order to apply the pause between 2 chunks, rather than having it applied recursively during traversing the tree? The way this works, and I'll show it to you here, is by adding the pause explicitly as what we call a personality annotation, which is another component of the actions, and this component has the type P. So we put that in here. Let's get the bracketing right, and let's see what happens now.
Given, we have x equals some division with square root 2a enumerator minus b.
Right. What you could hear now was that the pause was actually only applied straight after the denominator had been pronounced. Right. And that is effectively, in addition to this, we can also, for instance, change the volume, but I'm not going to demonstrate that now in detail. Instead, I'm going to demonstrate one final thing we can do with these, with the speech rules. And that was one final component one type of component for the action. And that is useful when you have a node where you do not necessarily know how many children the node has, and you want to recurse over all these nodes. And we'll do that given our division here. Right, and this component is of type M, which just stands for multinode, and you then give it a set of nodes. In our case, we select the set of nodes again with an XPath expression, which is just all subnodes, all child nodes of our mfrac expression. Let's do that. Let's see what happens.
Given, we have x equals some division with square root minus b plus minus square root of b squared minus 4ac 2a math.
Right, so what you could hear now was that all the elements are actually being pronounced properly, and this time in order, because this is just the regular order within the MathML expression. And now, obviously, for an expression like a division where you really know that you only have 2 children, this might not make a lot of sense. But if you do not know exactly how many children there are, say in the matrix expression we've demonstrated earlier, you might you have to use this way of accessing the children, and then you have in addition the opportunity or the possibility to put in something that is being spoken in between all of these expressions. And this is what the last thing I'll demonstrate to you now is by giving what we call a separator string as an further annotation to our component. And the separator is yet just a regular string in this case. And let's just say divided by, let's spell it right. And see what happens now.
Given, we have x equals some division with square root minus b plus minus square root of b squared minus 4ac divided by 2a math.
Right, and back we are at the original expression. Right, so this so far is the explanation of this API. And why did we go in that much detail in order to demonstrate you how this API works? Well, the basic idea of ChromeVox is, since it is an open project, that we're hoping that people will exploit this API in the future in order to write explicit speech rules, say on their web pages, to make sure that the math they write or they put on the web is pronounced in the right way. And for instance, I personally, as a university lecturer, university professor, could imagine that I'll put some of my lecture notes on the web, and since I do know exactly how things have to be pronounced, I also put speech rules there. So my students with visual impairments can actually go there and listen to the math in the correct way, in exactly the way I would speak it in my lecture. Right, and with this I'll end my part of the presentation and pass back to David, who's going to conclude with some more details on Chromebox and the project.
All right, thank you so much, Volker. I wanted to conclude by thanking everyone for watching and sticking with us through all of our demos. You can find a little bit more information about ChromeVox on chromevox.com. And we are an open source project, so you can actually even take a peek at all of our code, including all of the things that make math possible. We'd be happy to take any feedback that you have. You can also visit us in general for accessibility at Google at the address google.com/accessibility. Thanks again for watching, and hope to receive any feedback that you have. Thanks.